Thank you, everybody. I see at least a few familiar faces, so hi to everybody and everybody else as well. Um, so, yeah, thank you for the very kind introduction as well. So what is depth sensing? Essentially, it's a way to enable machines to be able to see the entire environment around them, just like humans do. That's the fundamental concept. And you do it by measuring distance to objects, humans or otherwise, obstacles along the way, and then you generate 3D maps. That's the fundamental concept. Typically, you need a specialized camera. Generally, what that means is you need to have a TX associated with a sensor. Like 2D cameras, typically you have a sensor, you've got your lens, you've got your optics, all the other passives, etc. Depth sensing generally come with, some sort of a TX partner, if you will, except when it comes to like passive stereo, and we'll talk about that. So the applications are endless. I think most people here understand that. Yeah, so I think I'll just go to the next slide. Okay, so this is what I call the tree of light. These are all of the various technologies that I've looked at as part of my role both at Apple and at Meta now when we're thinking about products. Obviously, there are non-optical approaches like radar, etc. I'm going to focus more on the optical approaches. You've got stereo, structured light, time of flight. Time of flight itself is pretty vast, right? You've got ITOF, DTOF. LiDAR essentially operates based on DTOF principles. But of course, I think I called it out separately because it's a different market space, right? We're talking distances, solid state MEMS, flash LiDAR. There's the FMCW, where you essentially have a CW transmit, but you modulate it in frequency and generate a chirp, and then you do optical mixing to create a beat frequency. So that's a little different. But I think generally when it comes to consumer electronics, most of the products that we're familiar with, you'll find are probably using a combination of somewhere in here. You'll hear me use the term point cloud from time to time. It's nothing more than the 3D location of an object in space. So with that, let's go to passive stereo. This is probably something we're all essentially familiar with. A target is imaged by two cameras, just like our eyes. You create a disparity map by essentially trying to pinpoint exactly what the pixel point of a point is for the image pair. And then the difference in distance between them on the image plane, that gets you the disparity. Disparity is inversely related to depth. The fundamental operating principle or equations really tells you how the system works. You've got the focal length, you've got the baseline, which is the distance between the camera pair, and then the disparity, which is on the denominator over here. If you want to minimize range errors, these are the general ways you can do this. So where would you use this? Maybe that's the first question to ask. For us, we think of it as if my system, my product, comes with two stereo cameras anyway, then that's the first place to start. Is that good enough? Why add the complexity or the cost of something else on top of that if my system needs these two cameras to begin with? So that's the first question you ask yourself. Now, there are obviously problems here with passive stereo, and let's go into what this means for the actual camera or the image sensors themselves. So I think generally, you can take the example, I'll take the example of the Quest 3 here. You've got the two cameras that are basically, spaced, the IPD, about 62 millimeters, slightly different, there's a range there. What are the things you look for? In general, I think when you're looking at depth sensing, you're probably trying to target a minimum resolution of QVGA. That's a minimum resolution where you start seeing a difference. So with that in mind, you have to think about what is your binning strategy of the pixel itself, what is the pixel size, the sensitivity, etc., that comes into play. And also, once again, if you're using the same cameras just for something like pass-through or just imaging, then you have to also, you're thinking about that camera. What does it look like in terms of sub-pixel disparity, et cetera, calculation? What is the algorithm you can use to get really good quality depth? I think some of the things that we look at, if you think in terms of RGB cameras compared to like monochrome cameras, you'll generally find that low light performance starts to degrade faster. Monochrome cameras are a little better. The RGB cameras, they start to degrade faster, so low light's not that good. So those are some of the basic things we look at from the sensor and the camera itself. In terms of field of view, what do you need? I think generally, if you're looking at, let's say you've got scenarios where you're basically, it's a pass-through. You're seeing the real world in your glasses or your headset in this example, and then you're just playing a game. You've got this ethereal environment that's created, and you're playing a game. In that scenario, you need to worry about safety because you're not able to see everything around you. Your kid walks across the room, your pet does the same thing. There's just a chair in front of you, et cetera. So that field of view becomes important. Generally, you're looking at something about 100 degrees. I think I have it written somewhere here. Well, if not, it's about 100 degrees for the field of view. Oh, there it is, yeah, for the overlap. And in terms of frame rate, et cetera, I think faster is always better. I think that's where you start. The problem comes here with what does this end up costing in the software domain? How much is my machine learning algorithm costing me to essentially have a DSP on the SoC, et cetera, et cetera? That becomes the challenge. It's power, it's latency, it's cost, it's heat. All of those things become a problem. So then you ask yourself, are you just better off having a dedicated depth sensor, to aid this situation? So the first thing you do, I already talked about the low light problems that you can encounter if you just use a stereo pair. Well, why not simplify the system by just adding like a projector? If I just add a projector, it creates a pattern, especially in low light. Think about this textureless wall, for example, white wall. It's perfect. I've got a pattern now, and I can use that to co-register features. Stereo matching becomes much better. Once again, though, like we talked about, the algorithmic challenges that come in ML, they don't go away. And on top of that, there is a limited benefit in terms of what you can get from the projector itself. If you look at this curve, it explains it pretty darn well. Generally, the precision, if you just go through the equations, what you find is you've got a part of the equation that shows that you are dependent on the actual pixel size and the algorithm that you use. And then there is a dependency on the SNR itself, which degrades with distance. So fundamentally, even with an active stereo system, if you will, you are still limited as far as how much range you can get from that system unless you start blowing up the TX power. I think I summarized this on the next slide. Okay, the other thing, I'm not going to spend too much time here on this slide, but generally in consumer electronics, what you'll find are VCSELs are traditionally the projectors of choice. I think in terms of the collimation and in terms of the control that you can get, they work far better than LEDs do. And then when you go into time of flight, you need to be modulating. So I think, VCSELs end up working out the best. Oh, yeah, this is what I was referring to. So in terms of an active/passive stereo depth system performance, what are the three most fundamental parameters that impact your system performance in the end? It's the pixel size, like we talked about. That's where the disparity comes into play. The baseline, obviously, it affects the range that you can actually hit. And then there is the optical power, like we talked about, which you're going to be limited depending on the actual system that you have. If you're thinking in terms of automotive, probably no problem. I think the Velodyne HDL64E, I believe, is just a huge honking thing, right? That just sits on top of a car and just keeps going round. No problem there. Consumer electronics, it's a problem, just like our friends from ST Micro talked about. We've also got a whole list of other parameters. You can take a look at this offline. What are the different subsystems and what specific parameter, these three parameters, do they affect. I think it's generally pretty good summary of what you can get in that. I think we'll move on from here to what a structured light system is. Structured light system is essentially very similar to a stereo system, except I just need one camera and I've got one TX. And I project a pattern on the object or the field of view, and the distortion is essentially captured by the camera. That's just very simply put how a structured light system works. The data obviously is then collected and processed, and you then build a model from that. In terms of the camera or the sensor itself, I think this is not different from the reason I don't have a dedicated slide on this one is because everything we talked about for a stereo system applies over here. You can use a traditional CIS pixel. You can get global shutter. No problem with that for structured light. The challenge with structured light is range. I think that becomes the fundamental problem. Can you really get 3, 4, 5 meters out of it? Probably not in a consumer electronics system. But for that range that you can get from it, it offers really good accuracy. I think that's worth pointing out for a structured light system. So I think we'll spend the next few minutes. Oh, I'll wait for that. There is something called an improved structured light system, which is really more of a dynamic one, where you can change the pattern on the fly. That gives you, more degrees of freedom as far as, getting the accuracy and the precision that you need. And that's fundamentally what that is. But once again, performance at range will always go down. So I think what we'll do is we'll spend the next 5-10 minutes on time of flight, and then we'll compare these systems as far as how we see it when we start looking at any particular product in mind. So time of flight fundamentally has two methods. I start with ITOF, which is the indirect time of flight, because I think it's worthwhile spending a couple of minutes on the SPAD itself. There were a couple of interesting questions on that topic in earlier sessions as well. Worth spending a little bit of time, at least giving my point of view as far as how we see it compared to a CIS pixel. But so an ITOF pixel essentially, or an ITOF system, fundamentally you're doing an amplitude modulation of light. And you use that phase difference between the transmit and the receive, and you convert that to time and then distance, et cetera, because you know what the speed of light is. That's the basic premise of an ITOF system. The receiver, like we talked about, can be implemented as part of a specialized sensor. You don't need laser scan, you don't need MEMS and things of that nature. It's pretty standard. ITOF does have some limitations as far as, at least this is what we believe. What we've seen is for our applications, it generally seems to have a little bit more of a multipath problem than, say, direct time of flight does. There is the flying pixels sort of thing where the background and the foreground, start to blend a little bit. And then most importantly, there's a dynamic range problem. I think that's just a fundamental problem that, moving to a SPAD-based pixel helps address. So I've actually got a slide that details how sort of the pixel itself, and I should say the sensor itself works. But essentially what you want is to be able, I think I put some notes in here, that you want to be able to disambiguate the signal. And for that, what you end up doing is you use the concept of multiple phases as far as what you put out. You have multiple taps on the pixel. There's a lot of papers out there that'll give you 4 tap pixels, 8 tap pixels, in fact. I'm pretty sure people here have probably worked on this as well. But I think just fundamentally speaking, you can see how these taps work. I think the concept of the tap is really that you've got one photodiode, but you've got multiple storage diodes, and then you can drain them. So it makes for a much more efficient readout system. That's the fundamental concept behind the whole taps and how you use it in an ITOF system. So let's move to DTOF system. This is about as straightforward as it gets in terms of you put a pulse of light out and you measure the round trip time. That's basically what it is. You have to use really short laser pulses. That is one of the challenges that we end up facing in the industry. And you need to have a specialized pixel, which is the SPAD pixel that you use for time of flight. You generate the histograms. I think that's been discussed multiple times through the last few sessions, so we'll not go too much into detail on that one. The one interesting thing about this is that this sensor or this pixel seems to have the most runway as far as where you can take it. In the evolution of the pixels and the sensors, etc., it feels like the SPAD has a way to go. With the CIS pixel, at least as far as being able to use it in consumer electronics, in the industry, etc., it seems like you're reaching that sort of point of no return, or diminishing return, I should say. So what makes the SPAD sensor special? I think first things first, I think we covered this in a few sessions, right? You generate a digital pulse at the time of each incoming photon. That's number one. You're able to basically measure the time of arrival of every photon. You know, you get around the dead time problem with active quenching, etc., but that's basically what it does. The digital detection means no read noise, and now I can process all of the individual events. That then allows me to disambiguate between and measure single photons, right? So what this means is now I can do really low light, and the digital measurement essentially gets rid of the concept of full well that you have typical CIS pixels, you know, we're all aware of, or well aware of. And that basically means I have a very high dynamic range system that I can essentially create with a SPAD. So for us, I think this is something that at least we see this as a very powerful sensor or pixel technology, and where it goes is something we'll certainly be looking at, you know, with a lot of interest. A few parameters as far as the important things like we talked about. I think I'll skip that for now. I think a bunch of people have covered how the avalanching works. One thing I thought was worth noting is you will find if you go to LiDAR systems, for example, they'll generally use APDs. They won't use SPADs. I think that's probably the one difference as far as what, you know, you can use just an APD instead of a SPAD. And the biggest difference is in terms, it's just not practical for consumer electronic systems, APDs. They're expensive. You're doing an analog conversion. There's power involved, etc. So I think a SPAD makes much more sense for consumer electronics systems. I think I've got maybe 2 or 3 slides. Yeah, so how do we look at this? Just if we were to generalize all of these various technologies into, you know, just a comparison matrix, what does all this look like? Where might you start looking at these? Again, for us, what we do is every product comes with its own set of very specific requirements, and all of the entire camera suite, both 2D and 3D, etc., comes into play as far as what that product will use. So it's not a straightforward answer. We generally think about each product and its needs separately before coming up with the final answer. But if you were to think in terms of where are the benefits of one over the other, etc., I think direct time of flight, the biggest problem with direct time of flight is the resolution. I think what it can offer today is low resolution, and you cannot get global shutter imaging like you can get with, say, ITOF and structured light, etc. That's fundamentally where you see that problem. But it has its benefits, obviously. You can essentially, the sensor can give you a point cloud directly. You know, I don't need an ISP like an ITOF system probably does. If you're able to get around the resolution problem, maybe you can limit how much machine learning or what is the role of algorithms, you know, in that system. DTOF systems are not perfect, right? They do come with pileup. I think we're aware of those concepts. So there is a world where sort of using the cameras that you have along with a dedicated depth sensor ends up being the right answer, but everybody has to study this on their own based on what their system needs are. I think there's a couple of examples here as far as what products use what, and I think you can generally take a look here. as far as how these things play out. It really explains this very well because it shows you that each product has its own set of goals, and they're trying to, hit a different market, different, set of people, etc. What do you benefit most from? And I think that becomes the play here, right? So that's a good slide that shows that. I have a couple of examples here. Again, this is for people to look at offline. This is, just an example of if you were to start looking at sensors for each of these various technologies, if you want to go online and take a look at some examples of what you might look at as a starting point, but this is not it, right? I think I have, in fairness, I have noted there's a lot of work, our partners from ST, AMS, OmniVision, Samsung, all of these offer solutions in a variety of these spaces. So it's not just, I think structured light's a great example where I think if you remember the HoloLens from Microsoft, that's what they use, and that was a dedicated PrimeSense sensor before Apple bought that company. I think I've got, one more slide that talks, just a summary. Look, there isn't one perfect solution. Every product, every company, you have to go through your own set of questions and queries and answers to come up with that final answer. In some cases, cost really matters. In other cases, the performance is king. All of those things come into play as far as what you might use. A self-driving car, safety is everything. That, there's no concept of a corner case. Every corner case can be the difference between life and death. So, it is a real case. So that's basically where all of these things come into play, and it becomes a tricky thing to say, you have to go use this one technology for every product. There isn't a good answer like that. What we can say, and I think this is the one thing I can say as far as how my company and how we look at this is that we look at depth sensing as a very key enabling technology in AR, VR, MR, wearables, that space. And we're constantly looking at what is the right technology to use and for which product. And that's something we'll keep doing. I think with that, if I'm on time, not bad. I can stop here and take any questions.
Thank you very much.